what I want to do today is talk a little bit about some work that we've been doing, some new work that we've been doing with my group that's heavily focused on the linkage between science, forest science, and economic development, and also strong linkages to international climate policy. So for most of my career, I've been working on basic research on the global carbon cycle, trying to understand the role of tropical forests in the carbon cycle and the sources and sinks for greenhouse gases due to changes in land cover and land use. But about 5 or maybe more, 8 years ago, it was clear that the science community, the international science community, had pushed the science of climate change to the point that there was very strong and concerted action on mitigation policy internationally through the Framework Convention on Climate Change and its associated body, the Intergovernmental Panel on Climate Change, which I was a member of. And so it was clear that the time was right to begin thinking about how the science could be used in this policy arena, and how the science could also be used in terms of some of the development-related issues. Now, we formed a program that Scott mentioned called Carbon to Markets, and I won't go into much of that at all today, but the heavy focus of that initial work was to link the science and the applications that we had been working on for 20 years to two of the most important critical problems facing the world today, which I would say are poverty, rural poverty, and climate change. And we were focused on developing some tools that use agroforestry and measurement and monitoring techniques to link agroforestry and agroforestry systems in for rural poor landowners and land managers into carbon cycle markets, carbon markets, and those sorts of things. So that got us really engaged in working to link the science to policy within this kind of international climate regime. So what I want to talk about today is something that's a little bit more contemporary, and that is this topic of now that the international climate agreements are recognizing the importance of forests and mitigation through forest activities, now what happens, all right? Notwithstanding the almost brilliant move by the United States government to get out of the Paris agreements, and I'm saying that, as you probably know, facetiously, but the rest of the world is moving ahead, and the science still needs to support what the rest of the world is doing. So this is still very, very much relevant. I want to first just throw up some credits of all the people that have worked on this in this department internationally. Jay Samak, I can't say enough about his work, our Indian counterpart, Swapan Mehra. Folks from the department like Larry, Leo Zulu in geography, Pascal here. I also want to recognize some of our Malawian colleagues who are actually here today and are now part of our department attending the university as graduate students coming out of the government of Malawi, working on both PhD programs and master's degree programs. Tangu, Dan, Francis, and Mike are here, and you guys will probably know everything that I talk about, and I'm incredibly nervous to be presenting it to you because you really know what I'm talking about and probably know all the problems and issues. We have our international partners in India, outside the government in social entrepreneur groups like the IRA Ecological Solutions and Vertiver, and in the government in the Forest Survey of India, the Department of Forestry in Malawi, Forest Research Institute of Malawi, and now we have some new initiatives in Indonesia. We have some new partners for a Lestari project at the University of Palangkaraya and Muhammadiyah University in Palangkaraya. And those partners actually happen to be here. 4 of those folks are here in the audience as well, visiting this week as we do some work. And many, many more people that we've worked with. I want to draw on some of the work we've done in India, Indonesia, and Malawi, but I'm going to really focus on Malawi a lot, all right? So, we all know that carbon dioxide in the atmosphere is increasing. It's now surpassed 400 parts per million for the very first time in the paleo record even, all right? Except if you go back millions and millions of years. Interesting enough, the temperature, the global temperature of the Earth is in fact changing. This is a very nice representation of the monthly temperatures reported and over this, a time series from 1880 to 2017. And you can see the blue are earlier dates, the red are later dates, and August 2017, the last date of record, is the second warmest August in recorded history. 2016 was warmer. But you can see that this progression is going upward. I don't understand why there's a popular discussion about the stasis in the record. I don't know if you've read recently, but there was a really interesting paper that came out in Nature last week or the week before, and it's been quite controversial, and we can talk about that in the Q&A period. But there has been some stasis in the record, but it has a secular trend going up. Both the ocean sea surface temperatures are rising, and so our land surface temperatures are rising. And this is compiled from Met Station data around the world. And you can see this most recent period of the record in the last decade, if you will, has really been going up very much higher than in the past. So these records are revealing that temperatures are changing. But the question is always, is this a natural phenomenon, or is this something that is caused by humans? Now, what I want to show you is an animation that what it does is it shows the temperature record over time, and then it shows the influences of various forcing functions on the record, both natural and human caused. This is a very interesting graphic that was done by folks at NASA, and I think you'll find it real interesting. It takes a little while, but I think it's worth it. So this is the observed climate record, global average. It's the temperature anomaly record. Shows something like this, similar to what I just showed you. Now that's the base condition, if you will. So what about Milankovitch cycles and orbital changes? This shows the temperature influence globally from orbital cycles that change, the so-called Milankovitch cycles. Didn't have much of an effect. What about solar irradiance and solar output? Has a small effect, right? So it has had a warming effect in the last century. What about volcanic eruptions? Well, volcanic eruptions is really messy. It can both warm and cool, but the overall trend has been actually through aerosol production to be a cooling effect. So when you combine all these together, this is what the record looks like. And the game here, obviously, is can you match up these forcings to the actual observations, right? And so here are the natural factors that look pretty good in early parts of the record, but in the latter part of the record is dismal compared to in terms of predicting the observations. So now let's roll forward into some of the others. This is land use, but it's not land use conversion. This is the albedo effect of changing land cover. And this has had a slight cooling effect over this record. Ozone, which is air pollution, photochemical smog, has had a much more pronounced influence than even many of the natural factors, but it's still not enough to account for the observations. What about aerosols? Aerosols is very interesting, very important. Aerosols is actually having a cooling countervailing effect. The Asian brown cloud, if you will. This is the smog and air pollution that's coming out of Asia. It's going around the world. So if you put greenhouse gases, this is the emission of fossil fuel combustion and deforestation together, you get a very significant close match to the observations, right? You put them all together, and this is what you get, right? You get the greenhouse gases forcing climate above the observations, but you have some countering forcings that cool. And when you bring them all together in terms of human factors, very good match, right? Very good accounting for the observations. And if you put them all together, because you should, there are natural forcings. If you put them all together, you can reconstruct the record. And why is that important? It means that we're probably doing our science right, too, right? We can account for the observations in our numerical models and other data sets. So we do have a problem here. It comes from NASA. Houston, we have a problem. One of the forcings, one of the major sources of greenhouse gas is land clearing, primarily today in the tropics. And this is the image that we're familiar with, probably. Cutting of these large, high biomass, high carbon stock forests, conversion to pasture and other kinds of low carbon stock forest with associated emissions. So we can use global remote sensing to do some very detailed mapping of where this has been going on. And we've been doing this for 20 years. This is not that new, really. But it's a great picture because it shows the different land covers and land uses and disturbances. The fire, the front of the fire that's burning, the degradation of the forest here from logging, you can see it's a slightly different color green, the intact forest, the newly converted pasture with grasslands, imperator grass or African planted grass. And that's kind of what the picture looks like in the tropics today. In terms of the life cycle of a forest, in this case Brazil, most of these pictures are from Brazil. The intact forest is here. It gets selectively cut, slash is burned, and you get this kind of situation here. So it's selectively cut for some economic and political reasons. These trees that are standing are not allowed to be cut, but eventually they do get cut. And then you get the pasture formation after it's planted, and cattle is raised. All right. So what's happened then in 2015 is more than 190 countries around the world came together for the annual Conference of the Parties meeting in Paris. And this was the first time that there were agreements that were forged following the expiration of the Kyoto Protocol. And it's interesting, and our main point here is it's important because for the first time in the Accords, forests were considered. Emissions from deforestation and degradation of forests were considered right along with fossil fuels. All right, but there were a couple of other kinds of impacts of the agreement. The country delegations met in December of 2015. New commitment round was put in place to replace the Kyoto Protocol that expired in 2012. The problem with Kyoto that many people recognize is that it did not include all countries, and it created a hard partition between what was called Annex I countries and non-Annex I countries. This is the industrialized countries and the developing countries, right? That was very difficult to work with. There were all kinds of mechanisms and modalities for bringing developing countries into the picture, but they were in a voluntary list, they didn't have to participate, etc. And it did not include the major emission sources from deforestation. And the work of the scientific community was clearly showing that the gains that you would achieve in Kyoto going forward would be erased by more emissions from increasing deforestation. Forests are the forest and agriculture, the second most important sector behind energy globally. So the COP21, the 21st Conference of the Party in Paris, brought a new opportunity for climate change mitigation with a global consensus. And the thing that made the global consensus work was something that was called an INDC. This is a real weird term, intended nationally determined contributions. It was an event, it was an instrument, a document that every country prepared for the COP, stating their intentions in their programs for climate mitigation. Okay, this is a voluntary effort. And because there was this kind of, you bring your best contribution to the table, right? And we'll all bring our contributions to the table with the aim of reducing emissions by a certain amount. The amount was pegged to the amount necessary not to exceed 1.5 degrees centigrade of climate warming. That caused most of the countries to reach consensus, and there was nearly universal participation, universal consensus by all participating countries, including the United States. So there was this idea of your contribution as a country, national contributions. This was initiated at the 20th Conference of the Party, and it was at the domestic level for many countries the first time they formulated a comprehensive vision on their own, not externally imposed like the Kyoto requirements, for addressing climate change, and it prepared them politically for Paris because it was done in a year advance. Countries came well prepared. At the international level, the INDCs served as an indication of their readiness to contribute to the global effort and to a successful outcome. So it was an easy entry point for most countries. So you can begin to imagine how ludicrous the discussion now is about not signing or getting out of the Paris Agreement, because it was completely voluntary, still is, all right? Now, following the Paris Agreement, the INDC, the intended nationally determined contributions, have to move into something that's called an NDC, a nationally determined contribution. So, the nationally determined contribution is actually the plan every country will put in place for both mitigation and adaptation. This has an important implication for what we call MRV, measurement, reporting, and verification. This is the technical arm of the international agreements. This is very technical. We'll talk about it more in my presentation. It's more technical than in any other international agreement there is, right? So the Paris Agreements created a transparency framework that establishes modalities and a framework for both action and support from other countries. It includes regular reports on greenhouse gas inventories. Calculations have to be done on a regular basis. Implementation of the NDCs and its status and progress, as well as support provided and received for various adaptation measures. So there's a lot of stock taking that goes into this. They move from they transition from the former system into the new system, and then there's a system of accounting yet to be finally determined, technically, but the Paris Agreement provides the basic principles for accounting of emission reductions. In the accounting for their emission reductions, the parties use the methodologies of the IPCC, which are very rigorous, very technical in terms of how you account for carbon. It's the kind of stuff that we're teaching people in our carbon certificate program, all right? Even if you're a forester in a developing country or another country, you still have to learn new tricks. So why is land important? I can skip through this. 25% global emissions. AFOLO is the main, agriculture, forestry, and other land uses, main source of emissions. The IPCC says that the land sector could provide as much as 26% of the cumulative mitigation by 2030. So not only is it an important source, but much of the mitigation, replanting of trees, managing soils, all these kinds of things would be very important going forward. Without actions in the land sector, it's impossible to keep the global temperature increases less than 1.5 degrees centigrade. As well, this affects people, and this is how we've kind of entered it. 70% of the world's poorest people depend on forestry and agriculture for their livelihoods. 1.6 billion people rely on forests for food, water, fuel, medicines, cultural traditions, livelihoods. And yet, a quarter of the world's forest and agricultural land is being degraded. However, at the same time, there's an increasing realization of the importance of systems of trees outside of forests, which I won't have time to talk about today. But this is an interesting area too. There's tremendous amount of woody biomass on land that is not forested, agricultural land, etc. And that's where people are. That's where agriculture is. So that's an important piece. And there's a tremendous loss rate over the last several decades. So let's turn our attention to Malawi, where we're developing a USAID project. MSU is part of a USAID project called Protecting Ecosystems and Restoring Forests in Malawi, PERFORM. Sometimes I wonder how it's performing, but that's what it's called. And the focus is to provide development assistance for RED programs in Malawi and work with stakeholders and partners in Malawi, in the Department of Forestry, in the ministries, and so forth, to develop their means by which they can do the measurement, the accounting, the reporting, and use quantitative measures for monitoring performance of their interventions in terms of halting deforestation and reducing degradation. As you can see from this figure, forestry and agriculture constitute 85% or so of all the emissions from Malawi. Now, there's small amounts, we know, it's a small country, but this is a country that's dependent on forests. So now let's turn our attention to RED. What is RED? RED is the international program framework for reducing emissions from deforestation and degradation. All right? I want to point out some highlights here. There are 5 key RED activities. Reducing the emissions from the deforestation outright. In other words, slowing the rate of deforestation. Slowing the rate of degradation of forests, too, which is a little bit more tricky to measure. Conservation of carbon stocks, sometimes referred to as avoiding deforestation and protecting stocks that would otherwise be lost and emissions would be associated. Sustainable management of the forest includes a provision for forest management, as long as it's sustainable. And then enhancement of forest carbon stocks, which means replanting or restocking of biomass in forest systems. So I'm going to skip that. Well, I better put that up. So if you want to think about RED Plus in its kind of comprehensive way, you can imagine this kind of diagram where you have the tons of carbon here and time along this axis, and you have a kind of a fake or pseudo-history that we're talking about, an example history of a piece of land. It starts out in intact forest. It goes through a phase of sustainable forest management, harvest and recovery, harvest and recovery. There may be a period in which the stocks are degraded, but it's still a forest. It's still considered a forest until the stocks are degraded, say, to a certain point that's predefined. And then it becomes deforested, and then perhaps it goes into agriculture, or maybe it's then replanted into forest again with periods of temporarily unstocked areas that are maybe harvested if you're planting for a fuel wood farm or something like that as your enhancement. So all of these pieces go into the RED kind of continuum. Conservation, forest management, reduced emissions from deforestation and degradation, and enhancement of carbon stocks, okay? So any kind of measurement system that you need to report on forest need to take into account your ability to do these measurements or these kinds of systems. So the key thing for any country that's developing its RED programs is it has to have 4 key elements. A strategic plan, a national plan. It has to have a national forest monitoring system that has the MRV pieces. It has to produce reference emission levels. Think of this as a baseline condition upon which they can compare and watch their progress. And then the development of a safeguard information system, which is primarily focused on 2 things: biodiversity safeguards and social safeguards. What that means is you can't just put in an intervention to halt deforestation or enhance forest stocks by replanting that has adverse effects on biodiversity or adverse effects on livelihoods or access or tenure. All right? So those are called safeguards that you need to put in place. All right? The key element here for us is this: the National Forest Monitoring System. All countries like Malawi are trying to build capacity for that. There are three key elements of our our National Forest Monitoring System. Three areas of technical, institutional, and human capacity that have to be built. The first is a satellite forest cover monitoring system. This is the system that provides national estimates of deforestation and degradation, quantities, locations, rates, maps. The second is a national forest inventory. This is a system of sample plots, like most inventories, that allow you to calculate the standing stock of carbon in your forests using allometric equations, standard methods, etc. And then you have to have a piece in your government in which you can take all this information and calculate your greenhouse gas inventories and be able to report using standard IPCC methods on a regular basis. So what we're doing with our partners in Malawi is helping build capacity to put all these pieces in place. All right? Most countries don't have this. All right? Safe to say that technically speaking, no countries have one. Even the United States, but I think the United States could put one together pretty quickly, but this still has to be developed in the context of the Paris agreements. Skip that. So if you go back to the agreements that have come out of a long series of negotiations and discussions within the international framework, you have a series of decisions that define what a national forest monitoring system is. All right, this originally started at the Copenhagen Accords in 2009. It's three pieces: a combination of remote sensing and ground-based forest inventory approaches for estimating anthropogenic forest-related greenhouse gas emissions by sources and removals by sinks, forest carbon stocks, and forest area changes. It's measurable, has to be measurable. The second piece is you have to provide estimates that are transparent, consistent, as far as possible accurate, and reduce uncertainties, taking into account national capabilities and capacities. This is a reportable piece. And then thirdly, transparent, and the results are available and suitable for review externally as agreed by the Conference of the Parties. This is the verification piece. So this is the capacity that has to be built in Malawi and other countries, in India, Indonesia, where we're working. This is why I say, like almost none of the other multilateral environmental agreements, like the Convention on Biodiversity or the Convention on Desertification, this is highly technical. And let's walk through that a little bit. So we're going to look at Malawi just for you guys that don't know where Malawi is. That's where it is. It's in South and East Africa. So we're working on a national forest monitoring system. First, the Satellite Land Monitoring System, or SLIMS. Some comments about the Miyama forests in Malawi. The Miyama forests in Malawi are sparse woodlands, not closed, dense tropical forests like the Amazon, Scott. And I worked in the Amazon, Scott's right. And I find this really challenging and interesting. How do we get out in these woodland systems, right, and provide measurements? We'll talk a little bit more about that. But here you see that. These are the Miyama woodlands. Off in the distance, you see lots of land with trees on it, trees outside of forests, and then more Miyamba. So here's some pictures. Miyamba woodlands, whoops. Yeah. Just a quick survey from some of our surveys we've done in the field. It's dominated by the genus Brachystegia. And Dave McFarland has a lot of experience with those Brachystegia forests in Kenya, right? And it's, although no acacia in Miyamba, not really, there's some. But it's usually Brachystegia and Julbernardia, right? But yet it's still a very diverse forest because, look, you see number of species identified, 78, 55, 47, but it's really dominated by Brachystegia. Now, what's interesting about Brachystegia? I should ask a student the question. Just looking at it, you can tell there's not much classical merchantable wood there, right? So what does that mean? It means they're considered low-value forests, right? What's the other piece that's considered here? There are no reasons to measure it because you can't sell it, right? So what does that mean? Lack of allometric equations, lack of studies on demography and populations, all the stuff that we take for granted in temperate forests don't exist. Why? Because they look like this. Now what happens? Now they're valuable because they're carbon, either as a source that you don't want or as a potential sink through mitigation. So now we have to figure out how we're going to measure these systems. All right, just more examples from the field. The other piece about these systems in Malawi and many other countries that share this Miyama woodland that goes all through southern Africa, it's a huge, complex woodland system, is they're not really being deforested. That happens, but one of the big drivers of change is degradation. And in these pictures, we see degradation for fuel wood production. 80% of domestic energy in Malawi and many of its neighboring countries is from charcoal and fuel wood, right? So these systems get degraded. This is still a forest, but it's a degraded forest. This is just a pile that goes into an earthen kiln that will be made. This is our colleagues in Leo Zulu from Geography Department. So how do you measure that with satellite imagery? Most of the work that's been done that everybody talks about was done with closed forests like in the Amazon or Indonesia, Congo Basin, all those problems are worked out. How do you work in these woodland systems? All right. This is an example of charcoal is also a livelihood. Charcoal's a livelihood. So I'm just teasing with ideas like if you want to think this is a simple problem, it's not. You know, it's the only source of domestic energy. It's a main livelihood piece. So anyway, some pictures. These are fuel wood guys that are bringing wood out of the forest on their bicycles with a special contraption. Pretty cool. Pretty hard work, though, too. All right. So we need a remote sensing piece. I won't go into all the details. But this is the electromagnetic spectrum for vegetation. And what you see is you see the chlorophyll absorption area here with the pigments, and then you see the strong red edge where you have high reflectance of the near infrared. So this is the apparent reflectance, this is the wavelength, and you see that there's a big difference between this, and for a long time we have used in the community something that's called a vegetation index or normalized difference vegetation index. In this case, it's the near infrared value of a measurement, a pixel, minus the red value, because red is in here, divided by the sum of the two. All right? That's a long-standing kind of vegetation index, been around a long time. This shows an example of how that works. So here's a healthy tree with lots of leaves in a dense forest. It's just a cartoon, but imagine that's a dense forest. This is a senescent tree, a diseased tree, or degraded forest, right? And so what you see is there's lots of infrared reflectance, less visible reflectance, and so you have this ratio of 0.5 minus 0.08 divided by the sum. You get 0.72, high value. But in these degraded trees and systems and areas where you have more visible reflectance compared to near infrared, you get 0.4 minus 0.3 divided by the sum, you get 0.14. So this way of comparing the VI, the vegetation index, of different kinds of systems in place allows us to build what we call continuous fields data sets. And I'll talk about that. This is an example for the whole continent of Africa. So it doesn't look like a classical classification map, does it? Like Koppin's classification or a life zone map. It's a continuous field. All right? Now, a new technique that's been developed in the last 10 years, we've been working on this a lot, we've got a lot of published papers on these techniques in tropical forests, et cetera, is something that's called N-member modeling or spectral mixing model or N-member pixel unmixing. What it basically is based on simply is that you got two bands, right? You got one NDVI or one spectral band and another, and you find the ratio of the two. You take a lot of samples from the imagery. Each one of these would be a sample pixel or cluster of pixels. And the models basically says that if you're, say, right there, right in between end member A and end member C. What's an end member, by the way? An end member is a pure pixel. In this case, it might be a pure soil. Well, it might be pure soil. Up there might be pure vegetative cover. Usually we build models with two end members or a third. This might be non-photosynthetic vegetation, right? Those are pure. That is, if that pixel was all soil, it would be like that. If it was all vegetation, it would be like that. But if it were mixed, it would be right there. And so all these combinations of mixtures allows you to define the fraction that is green, or develop a fractional cover index from the vegetation index. And that fractional cover looks simply like this. You just take the absolute measure minus your open end member divided by the sum of the open and the full canopy member. I'm breezing through it, I know. And so you can move from these class maps like this to these continuous field product where you have fractional cover going from, some amount, in this case 60% up to 100%, right? So what does that do? That allows you to do a lot of stuff that you need to do for red, we think. We're working on this with our Malawi partners right now. And let's walk through that. So you take two dates in time. This is 2010, this is 2015. This is a mosaic of Landsat satellite imagery for the country of Malawi. Red is the forested areas. Non-red are the areas of customary land or agricultural land in Malawi. And then you compute for all pixels for the whole data set the fractional cover values, right? And it's a continuous field map now. And now, by comparing the two, so you can get a landscape map that looks more like this, right? So you see the forest in various fractions of cover or forest vegetative density. You see the land that's agriculture or customary land, but there are trees there too. You can see them in green, right? Not as dense. This is a cloud though. This is a closed canopy forest, a very rare occurrence in Malawi, in these woodlands. This is a tropical forest with lots of ficus in it. It's a very different system. But look how dark it is, right? So you can now get this continuous fields that allows you to kind of estimate what the landscape looks like in terms of forest density, carbon stock density over the surface. And then if you're able to look at 2 points in time, you'll get a high fractional cover minus a low fractional cover. You get a big difference. That's a change, all right? It's a quantitative change. Large changes are high-intensity changes. Small changes are low-intensity changes, like degradation changes. And then you can compute an intensity value of the change. And this then shows up in this area, areas of forest change, some of which are very minor, they're degradation. Some may be very high, they would be outright deforestation. Huge loss of fractional cover. So now with the continuous fields, you can actually start to beginning to calculate D and D, deforestation and degradation, which we were never doing in the Amazon work that I did. We never did that. It was all deforestation. Nobody does the degradation piece. The other thing that I have to reiterate on is that these are woodland systems. So you don't get this kind of like canopy cover that's dense and just 100% cover. You have to account for the fact that these are sparse systems. So looking at this fractional cover, even at one point in time, is extremely useful for that. Here's another place in Malawi where you see outright deforestation occurring over here, right? You see some encroachment or a hotspot of a community that's moved into the Parakese Forest Reserve on the top up there. You see a bunch of encroachment coming from this area up into the western part of Parakese for fuel and charcoal cultivation. And so you're beginning to see changes where they occur in these systems and also a measure of the intensity of change so you can begin mapping degradation. So here's what the forest map that the Malawi government uses in this area. This is the Liwonde Forest Reserve. The green here is the forest map. These holes are special cases of villages that were grandfathered in before the creation of the reserve. But this is what the forest map would have been, and this is what we're providing, right? So we're moving from these class maps to this continuous field approach so that you can then load it into an online system like this and begin showing for quantitative analysis and also to policymakers where the hotspots are, right? Where the hotspots are, and you can see this in Liwonde is a really good example because you have small changes within forest cover, but really hot changes going on in terms of the orange and reds kind of occurring in there. So we can quantify those, assign carbon stocks to them, and begin doing some of the work. So what we're producing are national reports on using these tools that are going into the national government, federal government, national government of Malawi. All right, now what do you need? The National Forest Inventory. So there we went through a process of design, series of workshops, looking at methods that foresters are using in Malawi, coming up with some documents on what methods for forest inventory could we use, and what would be the nature of the sample frame. There's some specific questions that we'd have to ask. Then we developed a prototype for 3 forest reserves across Malawi. And we set crews out in the summer of 2016 to measure to do the inventories in the heat of the summer of 2016. And 2 of the team leaders are here. 2 of the 5 team leaders, Mike Chirwa and Dan, who are now part of our graduate program. They led crews to go out into the field to do the sample. We developed standard operating procedures that have now been approved by the national government for establishing the inventory in the sample plots and for field measurements that you do at the plots, right? So it's a whole instruction and protocol set. We invoked a tool that we've developed online that estimates the number of plots that you need for a sample inventory, given your desired accuracy and precision. It's based on IPCC methods and something that Windrock International developed early on that my friend and late Sandra Brown really worked hard on it. It's a tribute to her life and her career that these things are still so important. And so you calculate how many plots you need. We spatialize those number of plots in a GIS using some random functions and produce an output product that comes out of the system that shows the locations of plots for the inventory. We then produce national maps at scale and projection that show, in this case, the Liwonde Forest Reserve, where the permanent plots should be put into the forest. These are all marked here. And there's a database that goes behind it that gives precise GPS coordinates. And the maps and the lists are distributed to field crews. In this case, we had 3 field crews that established about 100 points. Mike, how many points were there? 30? 45 maybe? I don't know, I can't remember. Lots, considering the work that has to be done. And then each map sheet looks something like this, where we can pull out of NASA the extremely high resolution imagery and locate the plots, and then they GPS navigate in the field to the location, right? So that's all set up through protocols and guides. And then the field measurements are done. And we set up, in this particular case, somebody like Dave McFarland might be interested in this, we set up a nested fixed radius plot system with cluster plots of 3 each at each location. That's why I say it might have been 45, but it's 3 times 45. And a number of measurements that are specified in the protocol guides on what to collect. Some of the measurements were for carbon and biomass. Some of the measurements were to validate the remote sensing. And so we come up with emission factors, mean above ground biomass in tons of carbon per hectare, below ground biomass from an expansion factor, and deadwood, and then this combined emission factors, then the total carbon stock estimated from the sample for the whole reserve. David, I think you'd be interested in this a little bit, right? The deadwood piece, really small. Now, why is that? Because it's the nature of these systems? It could be, but I think mostly because it's been removed. Is that what you were going to say? Yeah, they're taking it out, right. So there's not much deadwood contribution. So that's a tricky piece in the sense that it should be accounted even if they're taking it out. And then without going into detail, then we go right to the IPCC methods and we get the equations that we need to plug in all the pieces. A for the remote sensing, the average above ground biomass as B, and then the FD is the fraction of biomass lost in the disturbance. And we can then provide a means by which the government can do its reporting function. We recognize, and I'll end on this, because we're running out of time, that this isn't something that MSU should go in and do and like a consultant deliver. That's not our aim. The ultimate aim is capacity building, and this is a huge challenge. So we developed a capacity building model that we started in India with some experience and really had a chance to run it out in Malawi in a really fantastic way, I think. We had a great time doing that. But it builds on both technical capacity and functional capacity. Technical is the field-based inventory, land monitoring, GHG inventory. It's the highly technical pieces that these countries have to do their inventory with remote sensing, biometry, and allometry and all that. But there's also this other functional capacity that has to do with the policy and legal piece, forest management, partnering, and we developed a capacity building program around that with 2 target audiences. One was in-service professionals, like the folks that are here in our graduate program from the Department of Forest, but also another track on formal education. And so we have basic training and project-based. We do learning by doing projects. And then we have over in the associated universities across Malawi, we do large group engagement with seminars and work with their scholars and their degree programs as you're training the kind of next generation of folks to go into the in-service professionals. We've built a strategy that separates it into 2 ways. We have the satellite land monitoring system, developing what's called activity data, deforestation and degradation. And then we have the National Forest Inventory plot approach that devises what they call emission factors. We started with broad fundamentals, face-to-face lectures, large audiences, classic kind of stuff. Moved towards detailed discussions and presentations on methods and algorithms, and then directly into hands-on or field-based sessions. And then those went into a capstone activity that we're implementing this year and almost finished, where all those methods are turned over to the participants, the learners in the government. They have to build a prototype product that will then roll into a version 1 product that the government would accept. And what you see in Malawi and in lots of countries, they have 4 land cover maps already. World Bank, FAO, NASA, they're all done externally. But the game that we have to move towards is giving countries capacity to do it themselves, because the countries have to do the reporting on the NDCs. And so this piece is critical. And then we bring it all together. We haven't really done this yet in Malawi, training on reporting. And then it wouldn't be right if I didn't mention that we also have a formal education program, so we convinced USAID that we ought to have a scholars program where some Malawians could get resources from USAID to pursue formal education for advanced degrees. So we have here this year in residence, we have 4 scholars. I don't want to embarrass you guys, but we have 4 scholars from Malawi, professionals who are pursuing their advanced degree in PhD or master's as part of that structure. And so I had a whole bunch of things on the tools, but I'm going to end. Got a lot going on. I just want to end with so what? This is what I think. What is this all telling us? We have to have now the science community has to pivot. We have to start thinking about what I call actionable science. All right? What is actionable science? Well, I would argue that countries and communities do not need science results. What they need are specific tools based on the science methods. Specific tools that plug into these requirements. All right? Some people call them user-inspired science, translational science. MSU uses that term a lot, thrown around, translational science. We like actionable science. And this, I'm afraid to say, is not where the science community is. The science community still wants to do full carbon accounting. We're not going to do full carbon accounting. We're not going to measure soils in many cases, right? It's just too difficult. So you need to have these capacities, specific capacities for REDD+, not for carbon cycle science, but the best of what we've learned in carbon cycle science applied to REDD+ specifically. And for carbon management, enabling participation and compliance with the post-Paris Agreement. So that's what's next. And next is going to last quite a long time because we've got a lot of work to do. But I can see a lot of progress. And what I didn't show you is that in addition to this, we're developing some online tools, some snazzy cloud-based tools, handheld devices, all kinds of technology pieces too, but I just don't have time to go into it. But I think that this is where we're at in what we're working on in my lab. Trying to take all that 25 years of carbon cycle science off the bench and put it on the ground. So anyway, I'll end there. We have just a bit of time left for questions. So thank you for being patient.